Chemistry often treats the periodic table as a continuous, infinite map. We assume that as long as we keep adding protons to a nucleus, we will keep discovering heavier elements that follow the exact same predictable rules. The reality is much narrower. The periodic table is an island of stability, a specific geometric solution operating under highly constrained physical conditions. To see where this island ends, we have to look through the Relational Architecture Framework, or RAF. RAF is a mathematical model that treats physical reality as a network of continuously evolving relational states, rather than a collection of fixed, solid objects. Under RAF, the periodic table is a finite catalog. It lists the available boundary closure solutions, the exact geometric configurations where a system of energy can successfully lock itself into a stable state. This specific catalog of stable atoms only exists because it operates within a rigid baseline, the geometric rules of three-dimensional space, and the specific coupling mechanisms of the electromagnetic field. Because this catalog is constrained by geometry, it is mathematically bounded. There is a hard limit where the geometry required to hold an atom together collapses entirely. We can pinpoint that limit using the Rathe stability equation. An element remains stable only as long as its overall stability, S of Z, stays balanced. That balance is determined by dividing the core demand of the nucleus by the boundary capacity of its outer structure. When that ratio drops below 1, the system fails. Reconstructing the periodic table from these principles reveals the exact atomic number where standard chemistry breaks down. Applying that same mathematical limit to macroscopic structures reveals the exact engineering blueprint required to achieve room temperature superconductivity. Recognizing the periodic table as a bounded projection shifts the objective of physics. The goal is no longer finding smaller fundamental particles. The goal is engineering relational patterns. Standard quantum mechanics models an electron as a probability distribution, a cloud indicating where a tiny physical ball might be found. RAF discards the physical ball entirely. Instead, an electron is a continuous relational probability. What we perceive as a particle is actually a shifting, unresolved network of relationships. It constantly moves until an interaction forces it to snap into a stabilized pattern. Measurement causes state reduction, forcing those distributed probabilities to hold a single, rigid shape. This forces us to redefine the atom, abandoning the Bohr model of spheres orbiting a central cluster. In RAF terms, an atom requires exactly two components. First, a dense, fully locked central structure. Second, an expanding, mathematically incomplete outer boundary. We map these directly to standard chemistry. The locked center is protons and neutrons. The incomplete boundary is electron shells. That outer boundary cannot close in arbitrary ways. It has strictly limited geometric options for completing its shape, which forces it to repeat the exact same stabilizing patterns as it grows. The elements we observe are specific, repeating geometric solutions. They are physical manifestations of a system attempting to achieve mathematical phase closure. This explains a core mystery of chemistry, why the periodic table repeats in highly specific numerical intervals, 2, 8, 18, 32, rather than growing linearly. Those intervals are dictated by a boundary capacity equation. The capacity of any boundary layer is exactly 2 times the square of its closure order. Stepping up to higher closure orders generates the exact symmetry sequence of the periodic table, 2, 8, 18, 32, extending to 50. That numerical sequence is dictated strictly by the absolute limits of topological phase closure. It is a geometric necessity, not empirical bookkeeping. Inside that geometry, chemical behavior is controlled by the closure fraction. The closure fraction is the ratio of filled boundary positions to the total geometric capacity of that specific layer. At the extreme low end, the closure fraction is near 0. The outer boundary has barely formed. Being highly unstable, it readily acts as a donor, shedding its partial connections entirely to reach a stable state. At the center of the spectrum, the fraction sits at exactly 0.5. This creates a state of extreme flexibility, producing multi-binding behavior. Carbon sits precisely in this zone. At the extreme high end, the fraction hits exactly 1. This results in total boundary closure. The geometry is perfectly resolved, yielding the absolute inertness we observe in neon. All chemical reactions are simply the mechanical, geometric pursuit of frustration minimization between incomplete boundaries. Atoms bond to finish their shapes. We have to ask what happens to these geometric boundaries as atomic scale and nuclear size drastically increase. As the atomic number climbs, the internal relational stress of the nucleus increases. This translates to core demand, which grows relentlessly and proportionally with every added proton. This chart plots atomic stability. The continuous line shows core demand rising linearly. The stair-step line shows boundary capacity, trapped by geometric limits. There is a precise intersection where core demand outpaces boundary capacity, occurring roughly between atomic numbers 120 and 130. At this intersection, the internal relational stress of the core shatters the geometric limits of the outer layer. The boundary attempts to form the next geometric layer, but core stress prevents it from locking into place. The entire structure dissolves into chaos. The chemical consequences are absolute. Repeating groups cease to exist. Valence becomes completely undefinable. The structure suffers immediate phase instability. Beyond an atomic number of 130, matter ceases to be periodic. It ceases to be atomic. The periodic table is a finite, breakable construct. We can apply this exact same framework of closure limits beyond superheavy atoms, moving outward to macroscopic crystalline lattices. The ultimate macroscopic test of relational closure is room temperature superconductivity. Macroscopic coherence is dictated by the transport closure functional. This equation calculates if a connected macroscopic path maintains its phase geometry. Inside, we find opposing forces, thermal and lattice frustration variables, opposing the stabilizing phase-locking variable. Standard material science hunts for a passive room temperature superconductor, a perfectly balanced rock found in nature. The transport functional shows why that search is mathematically flawed. At room temperature, thermal agitation violently disrupts the system. The physical heat severs the glowing energy loops required for perfect transport. Passive materials inherently fail because thermal frustration breaks global phase closure faster than the material's geometry can maintain it. Relying on composition tuning ignores the strict mathematics of relational stress. RAF provides a specific solution. Room temperature superconductivity requires active topological design, not passive discovery. The goal is to build an engineered coherence habitat. This is a material and device system explicitly constructed to hold a coherent state together against the overwhelming burden of thermal noise. To achieve this macroscopic coherence, the system must cross a strict mathematical threshold. The ratio of topological lock support must heavily outweigh the thermal and defect scattering. Reaching this threshold requires specific physical conditions. The material needs a nested multiscale topology, combined with boundary conditions that are actively forced to phase lock. These engineered boundaries physically overpower thermal disorder. By rigidly deflecting the chaos, they force the internal network into a perfect transport closure. In this engineered state, matter exists exactly where its relational architecture is forced to close. The universe prioritizes stable relational patterns. Mastering the limits of those patterns is the definitive threshold for the next era of advanced physics.